Welcome back to DATQVAULT video lectures. This is lecture 4 in the series of stereochemistry. It's going to be the final lecture, and in this lecture we're going to quickly go over Fisher projections, how to draw them from a basic three-dimensional molecule, and figure out how they're useful in determining R and S enantiomers and diastereomers. So we're going to start out by figuring out how to actually draw a Newman projection from a three-dimensional representation of a molecule such as this one. So a Fisher projection is basically just a two-dimensional projection of a three-dimensional molecule. So if we want to take this molecule and basically draw it in two dimensions, but also retaining the same stereochemistry around the chiral center, what we do is we draw a Fisher projection of it. So to start drawing a Fisher projection, what we do is we kind of look down between two of the atoms on the molecule at the chiral center. And what we see if we look between these two atoms is one of the substituents is coming at us, and the other substituent is coming at us. So if we look between substituents T and Y, we notice that A and X are actually going to be pointed back and away from us like this. So to draw the Fisher projection, all that we simply have to do from this is just draw a cross like this, where substituents T and Y are coming out at us, and they're on the horizontal plane, and then A and X are the substituents pointing back and away from us, and those are going to be on the vertical plane. So let's actually take and do this with a real molecule. This example is 2-bromobutane. So to start drawing a Fisher projection of this molecule, again we're going to look between the methyl group and the hydrogen on this atom, and then we're just going to draw what we see. The methyl group is going to be facing towards us, and the hydrogen is going to be facing towards us. The bromine and this ethyl group right here are going to be facing back and away from us. So if we draw this, we see something kind of like this. Methyl group on the left-hand side, hydrogen on the right-hand side, and then we simply take away the wedges and dashes, and then we're left with just the Fisher projection of this three-dimensional molecule over here. So Fisher projections are really useful in helping us determine if a molecule is an R or an S stereoisomer. So let's just take this molecule right here in the three-dimensional form and figure out if it's R or S around this chiral center. This is a chiral molecule, remember, because it has 4 different substituents on it. So remember, we go from priority, bromine being the highest priority, the ethyl group, and then the methyl group. The hydrogen is the lowest priority substituent, and it's already faced back and away from us. So we just have to simply go from 1 to 3, and we notice we're going in a counterclockwise fashion. So this is in the S configurations. This would be S2-bromobutane. So when we look at the Fisher projection, we notice that if we're looking down between these two atoms, the hydrogen actually comes out and points towards us. So we're going to label the substituents in the same exact manner, and then we're going to rotate going from the highest priority to the lowest priority substituent. If you notice, in this case, we're actually going clockwise. But since the hydrogen in the Fisher projection on the horizontal plane always comes out at you, you just switch the configuration. So this would be R for going counterclockwise, but since the hydrogen is coming out towards us, it's actually going to be, again, the S configuration. So one key thing to learning about Fisher projections is the two substituents on the horizontal plane here are always come out towards you. So think of it as the two substituents acting as arms on this side, and they're just like coming out to hug you. That's kind of how I remember it. And then the two substituents that are vertical are just leaning back and away from you. So that's kind of how you do figure out RNS enantiomers and a Fisher projection. So let's move on to something a little bit more complicated and trying to draw Fisher projections of atoms with more than one stereocenter. So here I have 3 molecules. These are all stereoisomers of one another. So why don't you try and draw the 3 different Fisher projections of these molecules. So pause the video and then we'll come back and go through this together. Alright, so the first thing we do when drawing a Fisher projection is I find the longest carbon chain. So this would be 1, 2, 3, 4 carbons long. And so I'm going to take this longest carbon chain. I'm just going to make it the vertical chain in the system. Something like this, where this is carbon 1, 2, 3, and 4. Alright, so remember that this top substituent is always faced back, and so is the bottom substituent. So if we want to make this molecule look like these 2 methyl groups here are facing back, it might be easiest to draw it something like this. So now since we rotated around this bond, like so, this alcohol, this OH group, is now faced back, and the chlorine is still faced forwards towards us. Now, if we look at it from this direction, this is exactly what we see. The 2 methyl groups facing back and away, and these 2 groups are both on one side of the molecule. Alright, so we're going to put one of the CH3s up here, and the other CH3 down here. So if we're looking at it from this direction, we'll notice that the OH group is on the left-hand side. It's going to be over here. This chlorine group is going to be down here on the right-hand side. Alright, and this is carbon 1, 2, 3, and 4. Alright, cool. So now we're going to draw, these are hydrogens here, we're going to draw the Fisher projections of these other 2 molecules. I want to leave the dashes out of them this time. An easy way to go from one stereoisomer to the other stereoisomer is, instead of drawing the whole molecule like this again, we can just flip the position of these substituents around. So notice we're going from an OH being forward to the OH being back, chlorine being forward to chlorine being back. When you translate that to a Fisher projection, you just simply switch the substituent to the opposite side of the Fisher projection. So we're going to do the same thing for the last example over here. The OH is still forward in this one, so we're going to leave it on this side. And then we notice that the chlorine is now switched from being forward to back, so we're going to put it on this side of the molecule. Alright, so now we want to be able to make sure we got this thing completely correct and label the stereocenters. So in this molecule, these are both R stereocenters in here. These stereocenters, since this is the enantiomer of this first molecule, they're both S, and then this one has an R and an S stereocenter. Alright, so to make sure we got this right, the OH gets number 1 priority, this gets 2, and the CH3 gets 3rd priority. We're traveling in a counterclockwise rotation around here, but remember this hydrogen comes forward, so we switch it to clockwise rotation, and if we remember, clockwise gives us the R orientation. So we correctly drew the Fisher projection of this molecule. And if you look through and do the rest of them, you'll notice that this is indeed RR configuration, SS, and SR. So if you don't remember how to label S and R configurations, I suggest going back to that lecture and practicing a little bit, and then going through and confirming that these indeed are an S configurations. Alright, so now that we know how to draw Fisher projections and label them as R or S, we can easily tell if these are enantiomers and diastereomers of each other. So the first Fisher projection, if you switch both of the atoms around at the chiral centers, you will get the enantiomer. And then if you switch just one of the substituents to the other side, you will get the diastereomer. Alright, so let's go ahead and do an example. Here we're asked what the diastereomer is of this molecule, this certain aldehyde. So why don't you go ahead and figure out if A, B, C, D, or E is the diastereomer of this molecule, and then we'll work through it together. Alright, so just like on the real DAT, you're just given a whiteboard over here to draw on since the whole exam is computerized. So I suggest using a process of elimination. So we can look through these molecules, and we notice that for answer A, we're switching around 2 atoms at the stereocenters. This molecule has only 2 stereocenters, here and here. Remember, a stereocenter is a carbon center that has 4 distinctly different substituents coming off of it. And if we notice this carbon center right here is not a stereocenter because we have 2 hydrogens coming off of it. So we're switching substituents at the 2 stereocenters here, so that gives us a possibility of it being a diastereomer. Here we're also switching the substituents around at the stereocenter, so we have another possibility of it. Sorry, answer C, we're switching around the substituents, so it has a possibility of being a diastereomer. Answer B, we are just switching the CH3 group from being down here to here. That does not change the molecule at all. This is actually the exact same molecule, so we can cross that one off. Answer D, once again, we're just switching around the methyl group. That helps us not at all in determining if it's a diastereomer because it's the same exact molecule once again. And then question E, we're completely switching 2 of the atoms around. We're changing connectivity of the overall molecule. So that means it's a constitutional isomer and not a stereoisomer of any kind. So when we look at answers A and C, we notice that here we're only switching one of the hydroxyl groups from the right-hand side to the left-hand side. C, we're switching both of the hydroxyl groups, so C would be an enantiomer of this initial compound, while A would actually be the diastereomer here. Alright, so that's a quick overview on Fisher projections. They're useful in determining R and S stereocenters. You will definitely have the possibility of seeing a problem or two on Fisher projections on the DAT, so it's important to fully understand how they're drawn and how they're used. So go ahead and go through and do a few sample problems on Fisher projections to kind of solidify the ideas in this lecture, and we'll see you back here again for another lecture later.